Hi, welcome to the session 2 on the Core Java tutorial series. In our previous session, we started off with the JVM architecture, wherein we covered topics such as virtual machine, types of virtual machines. We have the hardware-based virtual machine, then we have the application-based virtual machine, then the basic architecture diagram of JVM. After that, we started off with the class loader subsystem, wherein we covered the loading part in detail. So for today's agenda, we have linking and initialization. So we will be going to cover this linking and initialization part in detail today. But before starting off with linking and initialization, let's do a short recap on the loading part. Yes, my screen is visible. So consider an example where we have a Java file known as test.java. We want to run this in our system. So what is the very first step we need to do? The very first step is we need to compile this test.java file. On compiling this test.java file, we get a test.class file. So what is the command which compiles this Java file? It is javac test.java. It compiles, this javac compiler compiles this test.java file and creates test.class file, which is also known as bytecode. Okay, so here we have this term bytecode. What is bytecode? Basically, this test.class file or bytecode is responsible for making Java a platform independent programming language. Do you know how? Okay. Basically, if you generate the bytecode in a Windows machine, or if you generate it in a Mac OS or a Linux machine, the bytecode is generated in different machines, all those different machines. The value of the bytecode or the contents of the bytecode is same everywhere. Okay. I'm talking about if you compile this test.java class in a Windows machine or a Mac machine or a Linux machine, the end result is same everywhere. That is, the bytecode is same, bytecode generated is same in all the machines. And this bytecode is actually fed into the JVM because the JVM won't be able to understand the code which we have written in this test.java file. It only understands bytecode. This is an intermediate language which intermediate code which actually JVM understands. Okay. So the JVM which is installed in Windows will be able to understand the bytecode of test class. Okay. JVM which is present inside the macOS will also be able to understand the same bytecode. The JVM which is installed in the Linux machine will also be able to understand this same bytecode. Okay. Therefore, you write the code once and you run it anywhere. You don't need to worry about which system it is going to run. Okay. This is the concept of platform independency. So here is a point to be noted. The JVM for the Windows machine is separate from the Linux machine, is different from the Mac OS machine. We have three different download options for the JVM or the JDK. Okay. So basically we have a JDK for the Windows machine. We have another JDK for Linux machine. We have a JDK for the Mac OS machine. So the JDK is different and we have JVM present inside the JDK. So the JDK that is installed in different systems there might be some differences, but the code, the input which it takes, it's same everywhere. Basically, so you can run this bytecode in any system, in any operating system. You don't have to worry about the underlying operating system in which your code is going to run. So this is the concept of platform independency of Java. Now let's get back to the topic. We were discussing the loading part. So we have this test.class file now. Okay. So so what is the next step we need to do to run this program? It is Java test. We need to execute this command Java test. What it does is it instructs the JVM to load this test.class file into some memory area which is present inside the JVM. Okay. So let me draw a rough diagram about the JVM architecture. So basically this is the JVM. The part in the right side of the line is JVM. Okay. So we have the class loader subsystem wherein we have three steps: the loading step, linking step, and the initialization step. Now let me draw the memory area. Okay. So in the memory area, we have five different memory areas as we know: the method area, the heap area, the stack, the PC registers, and the native method stacks. Okay. Our main point of concern for today's agenda is the method area and the heap area. Okay. So this is the method area and this is the heap area. So what the loading process does, it loads this test.class file here inside this method area. And the contents of this loaded class file comprises of the following exhaustive set of information, such as the fully qualified name of the class, fully qualified name of the immediate parent class, whether the dot class file represents a class, interface, or an enum, methods, constructor and variable information, modifier information, etc. But the information which is present inside the method area pertaining to the test.class file is not understandable to the programmer as it is in the binary form. So to have some information in usable format for the programmers, the only way out is having an object which has all the details of the dot class file stored inside it. So what happens simultaneously when JVM loads this test.class file in the method area, simultaneously an object of class file is created in the heap area. Object of class file for this test class is created in the heap area. Okay. It also contains all the exhaustive set of information, that is a fully qualified name of the class, fully qualified name of the immediate parent class, etc. etc. So the object which is present here, this can be used by the programmer to fetch information regarding the dot class file that has just been loaded into the memory area of JVM. Okay. Okay, so let's start with the agenda for today. So we have linking and initialization. Linking is subdivided into verification, preparation, and resolution. Okay, so what is verification? Verification is a process of ensuring that the binary code representation of the dot class file is structurally correct or not. That is, the JVM will check whether the dot class file is generated by a valid compiler or not. Internally, bytecode verifier is a part of the class loader subsystem which is responsible for this verification procedure. Okay. So we also have the concept of a magic number. So in the dot class file, the first 4 bytes are allocated for a hexadecimal number known as magic number. So the bytecode verifier checks if the magic number is present or not inside this dot class file for in the first 4 bytes. If it is not present, then it will show a verification error. Okay. So this is actually an error from the main class throwable. This is a type of error which gets thrown at runtime. Next on we have preparation. In this phase, JVM will allocate memory for the classes or for the class level static variables and assign default values to them. For instance, we have something like this. We have a class A, and inside it we have a static field, static int A equals to 5. So what will happen in this preparation phase? In the preparation phase, the static field, that is A, will be assigned to its default value. What is the default value of int? Default value of int is 0. Okay. So default value of int is 0 for double. If it had this been double, it would have been 0.0. Had this been a boolean, then it would have been false. So here in this, we are just assigning the default values to the variables in this phase. So one might have a question like, when will the actual values get assigned to the variables? It happens in this initialization phase, not the preparation phase. In the preparation phase, we just have like values such as 0 if it is int, or had this been double, it would have been assigned to 0.0, etc. So where this, like in which part of the JVM this memory for this static fields is allocated? It is the method area. So this A equals to 0 will be present inside the method area for now. Now let's move on to the resolution phase. It is a process of replacing the symbolic references present inside the class with direct references from the memory area. Okay. So as an example, we might have this. We have a class student. This is the definition of class student. And then again, we have class teacher. So inside this class teacher, we might have reference to a student object. Student S equals to new student. So in this phase, what will happen is the student S equals to new student, S will be replaced. S is a symbolic reference. S will be replaced with the actual memory reference. Okay. So this is basically what happens in the resolution phase. Okay. In other words, now let's move on to the initialization phase. So what happens in the initialization phase, as I stated earlier, in the initialization phase, these default values, these fields which have been assigned to the default values now will be assigned to their actual original values. Okay. So what will happen? A will be assigned to 5 in this case. And all the static blocks will be executed from top to bottom, as in the parent class static blocks will be executed first, then on the child class static blocks will be executed. Okay, so this is all about today's session, wherein we covered linking and initialization. So in linking, we have verification, preparation, and resolution phases. In verification phase, the bytecode is verified, whether it is generated by a proper compiler, generated by a valid compiler or not. It is checked for structural correctness. Then on in the preparation phase, the static fields are assigned to their default values. Then moving on to the resolution phase, the symbolic names are replaced with actual references from the memory area. And in the initialization phase, those static fields which have been declared in the preparation phase will be assigned to their original values. And all the static blocks will be executed from top to bottom. That is, the parent class static blocks will be executed first, then the child class static blocks will be executed. Okay, so thank you. If you have any questions, you can surely ask me in the comment section. I would be happy to answer to them. Okay.